Now we get to the so what, or the executive summary, or the in conclusion points on each of the four areas. So we're going to talk about hardware, software, more like platform software. We're going to talk about applications, and then we're going to talk about the consultancies or ISVs out there. So many insights, so many points. So in hardware, we see that universal gate-based systems, think of them as superconducting qubits, were used to show quantum supremacy by Google, and they're used by IBM and Rigetti. They're also used by D-Wave and Intel, and so seems to be a leading technology. However, ion trap hardware is the focus of U.S. government grant money. Honeywell, IonQ, and Alpine Quantum Technologies, and others as well. So I wouldn't count them out as well. And ion traps had the advantage of not needing to be as cold. There's other quantum processing unit technologies that are being explored. Many of them could work. Photons, electrons, single atoms that are neutral, even putting your qubits into diamond, nitrogen vacancies. Actually, very, very good for quantum sensing right now. Quantum annealing is a specific analog hardware use case. It's for optimization. It's the sole domain right now of D-Wave Systems out of Canada, and we see simulation of this technology by Toshiba and Fujitsu. What's nice is this technology today can provide business value. I'm not going to say it runs faster than all the other computers in the world, but it probably runs faster than some of the applications that our clients are using today. So optimization around quantum annealing is a great short-term use case. We do see competitive performance on today's quantum computers. Most providers are offering access to their quantum computers via the public cloud. Only one company, D-Wave, is ship product. Really, no vendor has cracked the code on many of the elements of the hardware stack. So when you think of quantum RAM, which is um, memory that has entangled data and that keeps its entanglement, doesn't exist. I mean, only in a tabletop research center. Entangled disk, entangled tape, I/O, networking, operating systems, and database systems. Right, we default back to digital or classical systems. Um, the next point, most systems are accessed via graphical low-level programming languages or kind of code as you think languages like Python with open source libraries that are compiled at the machine level at runtime. And so they're making it easy to build applications or really functions. Um, we do see valuable white space in supporting the stack technologies that we talked about before. And then lastly, due to the bimodal split of hardware vendors, think of it as Fortune 100 versus the venture cap or private firms, we believe the smaller firms are most likely to get acquired by the larger firms as they find success and they're able to scale the technology. In the software platform stack, we see Microsoft, IBM, Intel, and Google have all open sourced their software platforms. This is a trend. If I open source, I get more people in, I get them helping to develop, taking the software in the right path. Now, D-Wave has Ocean, which is proprietary, but what I've heard from the CEO or US CEO is, look, the software controls and protects the analog hardware from damage, and so we have to control it. So Rigetti and Xanadu, not sure whether it's proprietary or not, but they do have their own stacks. One Qubit has partnered with Microsoft and they focus on chemicals and materials. QCware, we've talked about this before, as their cross-platform stack. It's agnostic to the different hardware providers and they sell runtime per hour. And we do see proprietary applications to help quantum computing makers do better. What's interesting is we see the applications, single use applications for a specific industry and a specific problem, taking a proprietary or licensing path forward. At Chicago Quantum, we think this is the way to go for small firms. If you can create an application that's reusable, you can find a way to pay your people and ensure your future. On the application side, again, building on that point, we see end user games, right, using, teaching, or simulating quantum computing. We see applications and libraries and algorithms and procedures being written and run via the Python language, very accessible. Um, Applications, mostly think of them as functions, can be written via gate operations. So you can swap qubits. You can throw qubits into a Hadamard and put them into a superposition or entanglement and start playing with the probabilities. The application code is compiled to run on specific hardware platforms, and it really matters. Sometimes the code has to be compiled for specific processors and methods, even parsed to fit on an available set of qubits. The programs are loaded, run, and results are provided in a binary string. There's no storage of your interim data, so there's no batch processing or checkpoint restart. You basically have to load all the data and do it all over again. Um, Due to short run times, less than a second, we need to write very short recursive programs with shallow logic strings. And finally, and we see this in Chicago Quantum, creating applications and solving business problems requires deep, multidisciplinary expertise to create the inputs, understand the requirements, generate the outputs, build the logic, and create a user experience that's attractive for our customer. Finally, what we see in the consulting and independent software vendor markets, we see very little activity in the public domain. Either nothing's happening, no one's hiring, right? Or everything is being done behind the curtain. We do see a few, what I'll call non-independent engagements, but very few independent engagements. What I mean by that is a company takes an equity stake in another company and all of a sudden they're using them for work. We see patents and proprietary tool sets. I think Accenture patented how to determine whether whether a business function or application should be running on a quantum computer. We see proprietary tool sets. We see this as an IP land grab, and it creates differentiation if those patents can be enforced. In our space, potential clients want to do joint research, or they want to support education programs. It's not so much they want us to come in and write code, they want us to help them do research and to learn. And today there's no killer application. I think of like SAP or other ERP apps or ServiceNow. There's no killer app to drive consulting around a complex quantum solution, at least not yet. So thank you for listening. This is Jeffrey Cohen, president of Chicago Quantum, which is a service mark brand of U.S. Advanced Computing Infrastructures Incorporated, an Illinois corporation. Again, thank you very much for listening. For more information, give us a call or check out our website. Bye-bye.